doubts also. Okay, so this is work which has been going on for some time. About 2 PhD students have worked in this field, phase field modeling, and the third one is starting, not on materials but on something on the biological front. So phase field applied to biology, Aravinda. And Shanti was the first person who started this phase field modeling in IIT Bombay, and he finished in 2013. Now he's a postdoc in Penn State, and also we had been having collaboration with Pinaki, and we had been getting verification of our phase field results through MDs, because there are question marks about this particular method, phase field method. Although it's quite powerful, but everything is not perfect. Okay, so this is the general plan. The first, so I will be talking about a particular version of phase field model which is called phase field crystal models, which we have applied to polycrystals, which is very particular kind of material and somewhat uncommon in the physics literature. And so we look at polycrystals, driven polycrystals, that is undergoing deformation due to different cases, due to shear, due to body forces like gravity and so on. And so most of the time will be spent in topic 1 and 2. In the general setup, I will tell you about the formalism, and then in the third lecture, half of third lecture probably, I will be able to tell you something about phase field applied to cell shapes. Okay, and this is all about dynamics. Okay, so now this is the general outlook about phase field modeling. Now phase field modeling is so whenever I mean people have been doing phase field modeling for a while, and so typically it is applied to liquid state. Okay, so wherever you have, so these are the typical variables. So you have some material and phi. So these are all space-time dependent functions. It could be order parameter, density. You could have also have a velocity field coupled to that, and both co-evolving. And there will be so momentum conservation equation involving V, and the phi dynamics, the order parameter will be governed by some free energy. And typically people look at non-equilibrium steady states and so on, depends on the context. And these are good for the, particularly good for the liquid state, because in phase field, wherever, I mean, if you have a object of finite size, which means there are interfaces, in those contexts phase field is very useful, because in phase field you can take care of surface tension, or surface tension comes in naturally, which takes care of the boundary. Okay, and so and also for cases where you have binary fluids like system, so phase separation, forming coarsening, such kind of things, phase field have found lot of use. Now MD simulation, on the other hand, people had been using it for a long time, and the good thing about MD is that it is expensive, both memory wise and time wise, but the good thing is that you can look at molecular interactions, a system where you have a definite number of particles, larger the better, and the phenomena that you are looking at are happening at the molecular length and time scale. So you will be having collisions among particles, you will have vibrations and so on. So all molecular scale events, and that is a problem also, because if you are interested in mesoscale events, I mean things which does not happen at the femtoseconds level, but let's say microsecond, then you have to do a very long simulation, and that has been difficult with molecular dynamics, although computers have become immensely powerful these days. So this difficulty has gone down. People are handling millions of particles, and also in time, very long times. And So there had been a version of phase field model which came up in actually early 2000s, which was doing a mix of both. So it turned out to be a very good model for solids, for describing motion in solid, and that too molecular motion. Okay, I mean here so in the standard phase field models it is continuum. So you have a density field, you have a velocity field, but all coarse grained in space. In this new method, one have been able to put in microscopic scale information, that is, let's say, arrangement of a solid, I mean arrangement of atoms in a solid, that sort of things into phase field method, and the time evolution happens at the diffusive time scale. So not microscopic time scale but diffusive time scale, and hence it is fast if you are interested in phenomena which is happening at mesoscopic time scale. For example, movements of defects or defect structures, dislocations. If you want to see motions of those objects, phase field is quite good. And in solids, typically the people had been doing this defect motion for a while in the engineering community, but there you have to create defects of different types somewhat in ad hoc manner. Okay? Now the advantage in phase field is that it happens naturally. Okay? So that is a big strength, but it has its problems also. So I will focus more on this now. So of course MD is the correct thing, because at the molecular level you are incorporating the molecular level interactions, and some macro scale phenomena may emerge if you have a large system and if you can run it for long time, whereas this is somewhat an effective picture. Okay. Okay. So I tried to be brief here, but the essentials. So this phase field crystal model is so there is a free energy. There is only one field. There is no velocity field. There is only this order parameter field phi, which could be density. Okay. Now the free energy has a Landau-Ginzburg part. So this part is very much what you see in normal Landau-Ginzburg theory, which gives you second order phase transition. This part in Landau-Ginzburg would be just grad phi whole square, but here it is somewhat different. So normally if it was just grad phi whole square, then what that would do is penalize fluctuations. Okay. So whereas here this structure actually prefers fluctuations of a particular scale. Okay. So in the Fourier space you can think of this as Q0 square, some preferred scale, Q0 inverse is some preferred scale, minus Q square. So this object will be minimized, I mean when Q is equal to Q0. Okay. So that means you are preferring a particular scale, undulations of a particular scale. Now you can see that you are just preferring a particular magnitude, you are not preferring any particular vector. Okay. So one can say that this is you are preferring a isotropic. So the Q0 is a thing which is isotropic. You have not put in any particular vector which will help you to form certain type of lattice. Okay. But I guess it was just an accident that they found that this when you simulate in 2 dimension, it has low energy states as hexagonal crystal, okay, which is known to be the minimum energy state. Now where is the crystal coming? So if you simulate this, what you find, I mean if you look at the lowest energy state, what you find is that you form a hexagonal crystal. So this density field, the equilibrium density field, the energy minimized density fields has peaks. Okay. And if you say that the peaks at the location of atoms, then the arrangement of peaks is on a hexagonal lattice, okay, with 6 coordination number 6, or triangular lattice actually, not hexagonal lattice. Okay. And so that was somewhat an accident, and also in 3 dimension somewhat more complicated forms can give you FCC, BCC, those kind of structures. which was gotten somewhat accidentally, I would say, because you are preferring a particular scale but not a particular vector. Okay. When you get the hexagonal lattice, you have 2 unit vectors at 60-degree angle, and you can span the whole lattice using these 2 unit vectors. Okay. So those 2, I mean the system is preferring arrangement along those 2 unit vectors. That's the accident. That's not built in by hand here. The magnitude, the periodicity, the length is built in, but not the vector. Okay. So it was found that, and it was mainly pioneered by Martin Grant's group. So the first paper on this was in 2002, and they found a phase diagram which looks like this. So R and psi, these are some kind of scaled variables. So if you look at this, if this was just a in the simple Landau theory sense, this is just the distance from the the phase transition point, where you are having a second order phase transition in the Landau theory. If that term was not there, just grad phi square were there, and it would be a smooth transition. And this tells you how far you are from, when for example this is minus, you are in the solid state, and where you have some non-zero phi. When this is plus, phi equal to 0 will be the minimum energy state. Okay. So now delta T decides whether you are on the solid side or on the liquid side. So this parameter is proportional to delta T and other things. So below, when delta T is negative, you form you see certain phases, and so this is all constant phase, and below when delta T is less than 0, you do see solid phases, but there are 2 types of solid phases that happen. One is a strife phase, and another is a triangular phase. So the white thing is a strife phase. So in these regions you find the triangular phase. Just a second. Yeah. Now and these are the coexistence regions. Okay. So if you want to simulate a solid, you better be deep inside this. Okay. And if you want to simulate a stripe, you will be there. So that decides your choice of parameters. And psi tells you, gives you the information about the average value of rho. You can say average density in some sense. Okay.
Normally the solids you will see as vector.
Yes. In 2D, yes. Unless you create some external field, then it could be there, but not naturally. Okay. Now one weird thing, which is of course a negative about this model, is that you will see, so I'll show you some, wait a second, I'll show you some patterns first, and then we'll come back. Yeah, so forget about the writings here. If you look at the pattern, you will see hexagonal, 6 nearest neighbors, triangular lattice, that kind of ordering. And there are many of them actually of different orientation. So there is a patch which has certain orientation, there is another patch. So these you can think of as grains. Okay. Now this has been specially created. If you just take one nucleus, and then you can set an initial condition which is liquid like, let's say, all constant, phi is constant, but you choose the parameter so that your equilibrium phase is a triangular lattice, and then you put a nucleus like this by hand and then let it grow, and you will find that the whole system just fills up with a single triangular crystal. Okay. Now if you want to create a polycrystal, then you would put few nuclei whose orientations are somewhat random, and they will grow and they will merge, and you will get a polycrystal. Okay. Now so this is just to say that you get this sort of phases, which is a correct thermodynamic phase for 2 dimension. Okay. Now the weird thing is that, sorry, let me go back once more. If you look at the values, the particles are at negative values. So it is not the peaks, or rather negative peaks, which are identified as particle, which you can identify as the particle. Okay. So that is something weird about this, but this model can be somewhat tweaked, and you can set the value of rho always greater than 1, using some greater than 0 using some constant, so you can get positive peaks. But again, that makes the model more complicated. So people work with these negative spikes only and interpret them as particles. Okay, so this is already one weird thing about this model. Okay, now just going back. Now this model is, I mean, why this model gives you a solid is the reason is the following. That is, in normal solids, okay, I should also tell you one thing. This solid liquid transition is actually first order transition, as we know in normal 2D thing. And I mean, you can get hexatic phase and so on, such complications are there, but basically it's a first order transition. Whereas I showed you a Ginzburg-Landau Hamiltonian which gives you second order transition normally. Okay, but it turns out that because of this structure, which was first shown by Brazowski and then later on by Swift and Hohenberg, is that the fluctuations in this model, fluctuations around the preferred phase, makes the transition first order. Okay, so this is a very special example where although you have a Landau-Ginzburg kind of free energy, but the fluctuation makes the transition first order. Okay, I mean, as such, this model is not very good in order to study these phase transition behaviors, because I mean, the solid liquid to solid, because there are several odd things about this model. So according to me, it works pretty well in the solid state, but not so well. I mean, because so much is known about the solid liquid phase transition in 2D, it does not really produce all the details correctly. Okay. Okay. Now the reason the model works is that in a normal first order phase transition, you would have to put in, let's say, density functional theory of phase transition. You have to put in the correlation function, pair correlation function, whose Fourier transform is S of q, looks like this. Okay, I mean, this is actually experimental data, the dots. Okay, it oscillates and go down. Now in this theory, in this crystal phase field theory, you are just putting an approximation, that is, you are just approximating the first peak using this function. Okay, and you are forgetting about these ripples. These two are equivalent. So you are capturing some bit of solid like information, but not all the details, and that is the reason why it will not give you all the correct solid liquid transition characteristics. Okay. And the structure is somewhat special in the sense that you have to have q minus q symmetry, because you cannot, I mean, you have because the preferred vectors, if you choose, I mean, the a vector as your unit vector, minus a is also equally preferred unit vector. Okay, and fluctuations around q0 on both sides are penalized, which is made using this, because otherwise if the square was not there, sometimes it will be plus, sometimes it will be minus if q is more than the preferred q. So that's why this square, but at the same time they are not equally penalized, in the sense that this is not a symmetric function about that q0. Okay, this side and that side is slightly different. Okay, now you can look at dynamics of this system. So the dynamics is this. So you have a free energy and you want to conserve dynamics, in the sense you want to keep the total phi, which you could interpret as density, you want to keep it constant, mass conservation, if you interpret rho as density. So you will put that grad square, okay, with a diffusive time scale gamma inverse, and this is noise, and the noise is also conserved for the same reason. So you could, if you are interested in a equilibrium crystal, you could just start from this state and let this system evolve, and it will end up like this. Okay. Now why polycrystal? I'll come to that next. Okay. Now let me differ a little bit why polycrystal, but the model which I showed you was quite good for getting equilibrium crystal, equilibrium 2D triangular crystal. Now people found that these people mostly that this model is not very good for studying dynamics. Okay. Meaning when you are deforming the system and let's say you are putting a high shear strain rate or so, then the dynamics is not very well captured if you just keep this part. Okay. Because after all, these are diffusive dynamics. You have the atoms in your density field, but the dynamics that you are seeing is in the diffusive time scale. Okay. On the other hand, in real solids, when you put shear or other kind of deformations, the system relaxes, not necessarily in a diffusive manner. There are lattice vibrations. That is also one channel of letting the energy off. Okay. So these people, I would say somewhat ad hoc, in a somewhat ad hoc way, introduce this extra term, which is not really acceleration, but it is double derivative of phi. Now there is some justification, I would say rather crude justification why that term should be there, but their basic idea was that if you look at this equation and linearize, then because of this double derivative you will get sound modes. Okay. Now in normal hydrodynamics of liquids, let's say very simple fluids, there is this momentum conservation equation which is Navier-Stokes, and there is continuity equation, and there is also an energy equation. If you combine all this, you will get a second order equation in density, and it will show that there are damped sound modes as well as diffusive modes. Okay. So here also one is bringing in that feature by introducing this term somewhat ad hoc way. Okay. And these two parameters, they will be proportional to the sound speed. I mean, you can okay, let me try to explain that. I mean, the diffusion constant will be proportional to this. So to see that, just switch off this first term, forget about the noise. Now if you linearize this derivative, because the free energy starts with the quadratic and higher order terms, there will be a linear in rho term, I mean linear in phi term coming out from here. Okay. And then if this is off, you have a double derivative, and this is a double derivative in time, this is in a space. So this object will be sound velocity square. Okay. So from that one can argue that, actually one can show that this will be proportional to the sound speed, and similarly if you do not have that term, these two terms together will give you the diffusive dynamics. You can take beta here, and that will be the diffusion constant. Okay. Okay. Now coming to the justification of it. Justification is rather loose, I should say. So think of the momentum density, which is g, and this is the density, this is the velocity, and the chemical potential is this. So it's kind of a thermodynamic force coming from the free energy. So this is the momentum balance equation, and I have also assumed incompressibility, that is the divergence of g is 0, divergence of v is 0. Now so this is the thermodynamic force, and this is and these two together are coming from momentum conservation. Now you can manipulate these two, and so for example if you use a derivative here, space derivative, and use the continuity equation, you will finally come to this equation, provided you make certain approximations, some of which are somewhat outrageous according to me. So for example, this is not so bad, ignore the momentum squared term, which you regularly do when you do not have, I mean you throw out the nonlinearity when your Reynolds numbers are not high. Okay, so this is not so bad. Now adding a dissipation term is still also okay, because after all you are, I mean you are describing a Langevin dynamics, so that term you can add, and this is coming from the free energy, which is okay, but there is a rather drastic approximation that there will be one term here which you approximate as this. So basically you are saying, you are kind of expanding this around the constant rho. So if you expand rho, rho is the density field which has some mean value and some fluctuations, because you have these particles, the particles are your peaks. So if you expand it and just keep the constant, I mean just the average density term, then this is a constant and this goes in and then you get that structure. Now how good this is, I mean this is of course a quite a drastic approximation, but that gives you this equation. Okay. Okay. So given the derivation of this is quite murky, I mean people would not believe all that you get from by studying this equation for the solid. So hence there is a need to verify it in some other established method, which is MD. Okay. So I will not talk about MD today, but later. So today I will just for our system we will just take this equation and apply it for polycrystal to study polycrystals. Okay. Okay. So now once I am with polycrystals, so first question is why do I care about polycrystals? Then the various models of polycrystal for having a polycrystal numerically, that's not very standard. Then we will apply a drive to the polycrystal and which will generate defects, dislocations. We are in 2D, so that makes life slightly simpler. Only one kind of defects, edge ones. And then so these are the results that we get by applying this phase field crystal model to polycrystals. Okay. So which I will go just one by one. I don't think I will talk much about the last one. I may not have time for that. Okay. So essentially when we started this, I mean of course we didn't have these questions so well defined. We started this because I had a collaboration with a material science engineer in our institute, and we had a project from Tata Steel and we were trying to understand a very difficult problem, and soon we found that it's quite impossible to tackle that problem with the methods that we have, and then we kind of migrated to this phase field crystal model where the questions are much more microscopic, whereas the engineers, I mean in the engineering applications this is not of so much relevance. But still from the physicist point of view, one would like to understand microscopically what is going on. Okay, so that was our motivation. And then we started looking for various patterns of deformation and so on, and we found something interesting. Okay, now why polycrystals? Now that hardly requires an answer because almost all materials in nature are polycrystal. Okay, this is just a piece of rock in which you can see this kind of structure where there are grains of different orientations and so on. Now most of the man-made materials, metallic materials, they are all polycrystals. Okay, and the game is to design the material in such a way, smart materials, so that you can control this grain structure. And because this grain structure control your material hardness, ductility and so on, so forth, I mean basically almost all properties which are important for application, you would like to have a firm control on how to get a desired grain structure. Okay. Now at some point in 70s, 80s, people were thinking that the yield stress of a material goes up if you make the grain size smaller and smaller. Okay. Now so that's why there was a need to control this grain structure and to make grain structure as small as possible, meaning by grain structure I mean the mean grain size, let's say, as small as possible. But in 90s there was people found that at very small scale, that if you keep on making grains smaller and smaller beyond some scale, which is let's say several hundred nanometers, it becomes actually softer. Okay. So if you think of, so you are making your grain small with the hope that hardness yield stress will go up, but after you are down to some scale, yield stress goes down. Okay. And why does it go down? I don't think it's quite settled, and it's somewhat an open question, although people have qualitative understanding. So then what is good to have a grain structure which is not below this small scale, I mean this particular scale, which will make it softer. Okay. So and since it is that scale is at the like submicron or hundreds of nano, for bulk materials people don't really care about it so much. Okay. But for our simulations, since we can only deal with finite number of particles and less number of particles compared to what you find in macroscopic world, this is a good chance of looking at that regime where yield stress is not high. Okay. Although our focus is not towards that, we will look at small systems and we try to look for interesting deformation patterns. Okay. Okay. Now, in the industry, if you want to control this grain size structure, this is a very typical scheme. Is that, let's say you have this is just a cartoon diagram taken from wiki, that you have certain type of grain structure and you will put it into some roller which will make a grain structure out of it. I mean, you are making a sheet, thinner sheet out of this thicker sheet, and you are also modifying the grain structure, and you can do further heat treatments of various kinds to make what you want. Okay, I mean the grain structure. Okay, so this is just a cartoon, and in the engineering language, you would like to come up with schemes which will give you a desired kind of grain structure. Okay. Okay, so our focus is not that. So we are just looking at trying to look for interesting patterns in the deformation. But shear, the reason I show you that slide is that shear is a very important deformation that is applied to this kind of material. Okay, I mean it's a standard deformation mode. So you would like to know under shear how does this system behave. Okay, so we have this equation and we have to apply shear. Now in standard MD, there are various ways to apply shear. You put two walls and you keep moving those walls at constant speed and so on. Here that's not possible because you have a density field with you, and Goldenfeld's group came up with this particular scheme where they put a drift term here with the density field. So they are putting this velocity field by hand, although if you think of the system, you are simulating a system with some particles. There are no fluids in the system. Okay, but in this scheme, you are moving those particles in a well-defined manner. Namely, near the walls, you are moving the density field. I mean, you are imposing a density field, which will be a moving array of atoms, and the speed will go down exponentially from your boundaries. And you will hope that this scale lambda, this imposed velocity field for those atoms should not affect what's going on in the bulk. Okay, and we have checked in our simulation that that is quite true. So you can make the system size bigger in this direction, keeping the lambda same, and try to look for the invariance of the bulk behavior, which you find works. Okay, so this is not such a big culprit. Although when you look at the density field, there will be some effect of that, of course, near the wall. I mean more so near the wall and so on. Okay, so using this kind of drive to mimic the shear, that is moving walls. So they studied mostly avalanche dynamics. That means they studied defects in that you introduce in such a system by shearing. Defects come in through the boundaries and they accumulate. There will be a steady state, and sometimes there will be avalanche of defects. So defects will come in through the boundaries and so on. So which they analyzed and found certain power laws, which was I mean. They are also working for polycrystal. No, so they didn't talk about polycrystal. They apply a lot of shear and they find a disordered material here. Okay, so now of course. Okay. The thing is that applying lot of shear is not really the recipe to have a disordered state, because if your shear is too strong, what happens is that things start to slide. That is, in the bulk, things will order actually. If you have a polycrystal, it may actually go to a single crystal, and near the boundaries you will have lots of small broken grains which will take the impact of this imposed V field. Okay, so they didn't care about the I mean they didn't emphasize whether it's a polycrystal or not, but even in a polycrystal there are a lot of defects. In fact okay, we will come to that, but so this is the shearing scheme, somewhat ad hoc, but this is what it is. Okay, so here is a simulation which I will repeat. So this is a simulation of a bicrystal. You have periodic boundary condition with phase field model. So now there is a bicrystal. You see that dislocations, that is atoms are moving, and the whole system in the final state these two layers are moving, and the in between thing has become a single crystal. Okay. So in order to retain a polycrystal, you need a balance. You should not put so much of shear so that the system becomes a single crystal eventually. Okay. So if your shear is slow, you will find a polycrystalline state which will be a non-equilibrium steady state, and then you can study the defects and so on. Okay. Okay. So so this is a typical state. So here what I have done particularly is that you can see these hexagonal arrangements. Remember that these particles are nothing but peaks in your density field. Okay. And this so inside this it looks perfectly ordered, 6-fold symmetry, whereas at the boundaries you see this pink and red. So they are basically 7-fold and 5-fold coordination number, and they always come in pairs. Okay.
So here you are plotting the density fields or
just the location of the particles. Okay. So but the density field, if you plot, I mean, see, the density field is, so these are the locations of your minimas. Okay, and you are just following the minimas. So these are static configuration, so just the peak positions, and then you calculate the coordination number and you decide your color. So this bar is giving you local orientation, okay, which can, because it is 2D, it can be maximum. So misorientation between two grains, and you can see by bare eyes that the orientations are changing if you go from this to this. I mean, so for example, here it is like this, the lines of atom, here it is like this. Okay. So where the orientation changes a lot, you will have many defects, and where the orientation changes a little bit, your misorientation between this and this will be very small. I mean, you can see that lines are bending from here slightly. Okay. Now, so Frank had shown this long time back, that these grain boundaries, if you call these grains, are nothing but array of defects arranged in a very special way. Okay. So that's why, and higher the misorientation, more will be defect density, and so on. So in this simulation, what you see is that lots of small grains here and big grains in the middle. Okay. Now, so what we will concentrate on are, I mean, in this picture at least you can see the grains, you can see the defects, and you can see it's quite heterogeneous. That is near wall and inside quite different behavior. Okay, so this is our work which was published some time back. Okay, now we had been seeing this kind of pictures in the context of amorphous solids for a while. I mean, when we started looking for various kind of patterns of defects and motion in disordered material, we found many papers in complete amorphous material where, I mean, which had been obtained by these athermal simulations applying shear, is that so what you see at the V fields here, velocities, you don't see the head of the arrows, but they have plotted the, so these are all MD simulations that they have plotted the
so these are just
displacement fields. Yes.
Because in this case there are no velocities.
Yes. Okay. Now, now displacements in a very small time interval. Okay. So if this time interval is small, displacements are equivalent to velocity. Okay. So what you see here is that you see lots of vortices kind of pattern, and you see some patterns which has 4-fold symmetry, quadrupolar kind of symmetry, and if you could see the vectors, you would find that in two directions it will be unstable, that is arrows going out in two directions and arrows coming in the other two directions, sort of saddle, and these are quite commonly seen. Of course, because this is not a crystal, you don't see the, I mean, the underlying atoms are not really arranged in any particular fashion which you have in polycrystal. Now, the difference, a big difference between this system and polycrystal is that in these systems people struggle to find a characteristic scale. I mean, both in glass, amorphous material, lot of research goes in trying to find the characteristic scale, whether there is a characteristic scale. Now, on the other hand, in crystal, perfect crystal, the characteristic scale is infinity, everything is ordered. Polycrystal somewhere come somewhere in between, and the typical grain sizes gives you a characteristic scale. Okay. So, because of that, you do expect to see something different which you don't see here. So, here you can, I mean, these vortices etc. remind you of fluid type of motion, which you normally won't expect in a polycrystal, because things are solid, although various grains and so on. So, what do you get? What kind of motion do you see in polycrystals under shear? Here I am showing again velocity vectors, and these two regions I did not show because the velocity vectors will be very high here, the arrows will be very large, but in between you see lots of interesting type of motions. I mean, you see across the line there are some streak of atoms going in some direction. You can see vortices actually, and smaller the magnitude, smaller the velocity, and if you see closely you could actually see vortices, okay, which is very much liquid like, or at least amorphous, like amorphous material like. Okay. Now, but you don't really clearly see here those quadrupolar or saddle patterns which I just showed you. Now, it turns out those are present here also. So, before going to, just a second, let me just jump a little bit. Yeah, so let me just show you this and then I will go back. So, this is the same figure. We chose a particular configuration. You can see here there are regions where velocity vectors are going out here and coming in from the other direction. So, those so called saddles. So, this is a polycrystal, okay, and you do not make out seeing this that that there is an underlying polycrystalline structure, and of course, this will be happening, I mean this will be occurring at the boundary of those grains, not inside the grains, okay, because inside the grain things move in unison, okay. So, very ordered motion. Okay. Now, that was a surprise that why do we get this kind of, I mean it has been a question in the amorphous literature, amorphous material cases, that why do these special points happen, they are called hot spots and so on, why do they, I mean how do they come about, it is not understood, there are various theories and they pop up in various places quite randomly, and they are taken as precursor to strain release. Okay. So, big scale adjustments in strain happen after you see such spots, they propagate, they affect they have long distance effect as well, but it is not clear why they happen in amorphous material. Here it turns out we have been able to understand that using defect language. Okay, so I will just go back here. Okay, so, what I just told you is that it is, so here these are these defects. So, we tracked a particular, I mean emergence of a particular saddle type of structure in time. All these atoms have some velocity, and then we have interpolated those velocity to generate this continuous looking V field. Okay. Now, I mean this is part of the system, and then further we have gone to, you can see this is from 90 to 140, here is 100 to 125. So, we are focusing on this particular pair. Okay. So, these are 5-7 pair, they are approaching each other, and as they approach you can see the velocity vectors, it looks like a saddle, I mean going out in this direction and coming in this direction, and they will eventually annihilate. Okay. Now, so what we understand is that these kind of saddles, at least in polycrystals, happen because dislocations of a particular kind, I mean these defects come in a very special way, in the sense that they are annihilating. On the other hand, I have shown you grain pictures also where you found stable grains which were lined by these pink and red defects, but the difference between this and that structure is that is the arrangement of the defects. Okay. You can have them in a very stable arrangement, or you can have them in an arrangement when they will annihilate and create a strain field around it. Okay. So just to understand that, so this was seen in the simulation. So we just looked at how does this displacement field look like according to Frank. So who gave a theory. So this is elastic displacement due to a defect like this. If this defect was placed at the origin, if there was only one defect like this at the origin, then this would be the displacement field, ux and uy. Now what we found is that if you superimpose two such defects in this fashion, then you will generate this field. Okay. So essentially these things can be, so the emergence of this particular defect structure, this saddle type of displacement pattern, can be understood within polycrystal language as two defects of opposite type coming in a particular fashion and annihilating. Okay. Okay. So this is basically the simulation of that. It's not running, so I think, let's see. Yeah, it may run. So you will see the same thing. They will come and you see the emergence of the velocity field. I showed you the static diagrams. It's just that, nothing more than that. Okay. Now I showed you that, okay, there is a V field. Now this, of course, this V field is very, very small. You are shearing there and things are moving inside. Things are moving a little fast here, but very, very slow here. Now if you choose to calculate the average velocity as a function of y, let's say this is the y direction, you will find that there is a high velocities here and lesser velocities in the bulk. So if you plot that, you find the exponential. So this is imposed because you have to generate shear, you have imposed a exponential velocity field here. That's what this is. But there is an emergent structure of velocity field which is close to a power law, you can say, not very good, which is there in the bulk. Okay. Now of course the question will be that how much this is polluted by the effect of this imposed V field. Okay. I mean this exponential field. Of course that question remains. So what we have done is we have done bigger and bigger system and tried to see that you do get this kind of non-vanishing V field inside the bulk also. Okay. And we are plotting only half the system up to here. Because of symmetry, because this plate is going in that direction, this plate is going in this direction, at the mid plane the velocity is supposed to be close to 0 statistically, and that is what you see. So we are mainly having velocity in that direction as well as some small y component is also there in the V field, but I am not plotting that. Okay. Okay. So the velocity field has a characteristic structure. Okay. Now this is the displacement field. So here what we are plotting is the displacement. So this is the net displacement of a particle u, which has both x and y component, but we are plotting just mod of that. We are just looking at the magnitude. Okay. So x component must be the dominant part because the system is mostly moving in that direction. There is some small transverse part also. So the probability of that as a function of u for various times. So what does it mean? Now, so what it means is that I wait for 1000 iterations in some arbitrary units, let's say 1000 time. After 1000 time interval, what is the value of u of all the particles in the system? And this is a histogram of that. Okay. And if you delay the time more, so in a larger time you will have more displacement. Okay. So that's why these red ones, which are for 10,000 iterations, you find larger u's. Okay. And then you realize that that this can be collapsed to a single curve by the scaling. That is, this is the displacement divided by the time. So this is like velocity. Okay. And because of normalization reasons, this has to be multiplied by t. Then you find that all of them collapses like this. Okay. Now what it means is, see, what you know is that, okay, the reason it collapses is the following, that is the displacement u is mainly dominated by the x motion. Okay. And this is the v, and so I am ignoring the y motion altogether, and just the x motion will tell you will go as the typical velocity into t. Now note that this is not a constant, this is a function of y though. okay, but still it collapses, and the reason for that will be clearer in the sense little later. That is, I mean, just think of for a particular u value, let's say, so okay, now this quantity is more or less constant for all the particles which are at a particular y. Okay. Now, and because at a particular value of y, they contribute to some value of u by t. Okay. The ones which are inside, they contribute smaller u. Okay. So although this is a function of y, they will still collapse because the particles which are here, they have a constant velocity in the x direction in a certain interval of time. Okay. Sorry, for any interval of time. The velocity is this at a particular level of y. So y and u by t, they are connected. Okay. Now,
this outflow expression contains a contribution of mean flow.
this one, yeah. Now the mean is across this as a function of y. So this quantity is varying as a function of y.
So you did not investigate the non-pathing displacement, where you should abstract the mean flow velocity.
So
Yeah.
subtract the mean flow, then what is the
Fluctuations, you mean?
Yeah.
You mean? Okay, yeah. Now, yeah, fluctuation we did not look at. No, we did not look at. That could have been actually we have looked at fluctuation in a different context, but not for this system. We have not done that. Yeah. Now again, all that I am showing you, this is within this phase field formalism, phase field crystal formalism, whose basic tenet can be questioned. I showed you several flaws. Now it turned out that I mean, this is recent. This Zapiris group, 2017. They found with AC shear. So we applied a constant shear. They applied AC shear and looked at polycrystals, and they found similar looking graph that you can collapse them by doing this. So and of course they don't have these three regions which we had. This is MD simulation, but what they have is, I mean, if you notice the earlier graph, which I will show you, this was still to the power 1. Okay, and we have some reasons why it should be the scaling exponent is 1 here and some other minus alpha here. So we basically will I'll show you that this sort of scaling will come out from the grain rotation, and this sort of scaling will come out from the fact that the velocity field have this kind of scaling inside in the bulk. Okay. Okay, now you can see that these values of u, they are rather small. So rotations contribute to u, very low values of u. Okay, but okay, so so this graph basically they have the same thing, although they didn't talk about rotations as such, but so they didn't give any explanation for these either, and unfortunately they didn't. I mean, they didn't refer us for this diagram, showing that somebody else has seen this, although they have referred us for something else, but not this. Anyway, so so this was for different strain amplitudes. So they had a AC shear in this case, but this gave us some kind of confidence, gives us some kind of confidence that maybe what we are seeing through phase field crystal is not spurious. Okay, so this is a reasoning. Okay, how much time do I have? 5 minutes? Okay, fine. I'm almost at the end of. Okay, so this is a reasoning. Why do you get that linear profile? So I should maybe draw a graph and draw a small picture that will help. I should have put it here. I forgot. So think of a grain like this. Okay, in a grain, so you are shearing here. The plates are here. I'm just idealizing things. So particles are rotating like this. Okay. So the at different values of radius, the velocities are different. So velocity will be displacement, let's say, is omega 0 if you just consider a grain which is rotating at a constant speed. So this is the displacement in the azimuthal direction for the particles, okay, and these particles move faster, this particle will move smaller, and so on, okay, and all these small displacements will contribute to your P of u, which is the histogram of u, okay. Now if you take that and if you say that you are getting contribution to u, that is P of u, the contribution to P of u into du is coming from the strips. I mean, let's say a small strip of thickness dr will contribute a certain value of u, okay. So P of du is proportional to that area of that strip, which is 2 pi r dr, okay, and then you use the relation that you have and try to get rid of this r, then you find this, which is exactly the reason, and with a scaling exponent 1, okay. So we think that this is a signature of grain slowly moving, okay. Of course this is a very pure picture, you don't have this one grain, but in the actual experiment you do have small localized grains moving often. So we think and this velocity profile, I mean you can calculate in the same way, is coming from, or rather I would say that if you think of a particular velocity, that velocity will I mean the velocity falls off like this as a function of y, and the u in the same way, the u is velocity into time. So from this velocity scale, these I mean all the atoms that are at particular value of y, they will give you certain value of u, okay, and using the same kind of analysis you find that this should also scale like this, and this alpha is this alpha, how the velocity falls off, and that gives you 1.4, whereas from our numerics we find 1.2, and it could be because of various reasons, because of the boundary layer and so on. So this is a very somewhat a crude estimate, but I think this gives a idea that why this particular thing we get, okay. This thing again, I don't think that this exponent is universal for this particular system at all, because I will tell you later that we did the same thing for MD. I mean we simulated the same system with MD and we did not find any such well defined power law there, okay. So these things could be non-universal, but given that there is some support of that linear I mean profile Pu going as u for coming from grain rotation, I think that part will probably survive, okay. So I'll just summarize this part, that is so we have understood a process how saddles are generated in polycrystals, and the displacement distribution, that is P of u, is a good marker for heterogeneity in space time, in the sense that what we showed was that these different regimes are responsible for different kind of grain motion. So this is rotation, this is the thing which is happening in the in between region and so on. Now this portion which is very high u, we think are because of, I mean this is not coming from the boundaries, because this graph that you see, we have not taken into account the boundaries because they are very high, and also they are because you are applying a external field there, I mean external v field there. So these high things are coming from these high velocity spots that we have verified. So essentially these three different regimes tells you about the different type of motions taking place in different parts of the system, okay. So I will stop here, yeah.
Any questions?
Yeah.
Yeah.
Because your phase field model is so good that I cannot distinguish which
No, so far I did not show you.
All of them are fed by phase field.
Yes, yes, except this is not our data, this is Zapedi. That one is MD.
This one is
Yeah.
MD.
Rest everything, whatever I showed you, is phase field crystal model.
For two-dimensional case, this one.
Yes.
And this is very comparable to your phase field results.
Yes. Yeah, that is the point. Yes. Yeah.
Actually, even in the case of the earlier results that you showed from Antangi or Craig Maloney, etc., for the displacement fields in amorphous materials under shear. So the vortices and the
That was all ours, right? Which one? Right. Amorphous materials.
If
Yes.
you look at the displacement
Yeah.
field,
Yeah.
you get structures which are quite similar.
Yes. Structure wise similar, but yeah, qualitatively similar structure.
Distribution of displacements. Later on,
Okay, that I don't know actually. I mean, I haven't really checked what kind of distributions they find. I looked a little, but in those papers they don't really look at this particular object. Yeah. So what you are getting here is somewhat in between a fluid, or rather amorphous material and real crystals. Crystals have these defects, whereas you cannot define defects in an amorphous material. Okay, so I showed you that these hot spots are coming because of coalescence of these defects in a very particular fashion. So that is very much solid-like. You have these grains that is solid-like. On the other hand, you have this velocity field which is very much fluid-like, or at least amorphous material-like. So it's kind of a mixture of these two.
yeah, and the other point that Tapakra pointed out is one should also look at subtract the mean flow
And look at the fluctuations. Yeah. And so we have done a similar study for pressure-driven flow, and there we found that the fluctuations are non-Gaussian. I mean, they have non-Gaussian tails, but for this particular thing we haven't done. Yeah.